Mr. Harry, Mr. Runner, right? Okay, so let's say we have a binary tree, yeah? Binary.
Yeah.
What's binary tree? What's tree?
Is basically a tree, obviously. Upside down.
Okay, so what's the difference between a tree and a graph?
Tree is a graph.
That's excellent. Tree is a graph, but graph is not necessarily a tree, right? So for a tree, it does not have cycles, right? And then what else?
It also
What? Directly a cyclic
has
graph.
to
Right?
be connected.
Be connected where down. If it's different, then what we call it like forest. Okay. If each of these is a tree, then we call it a forest. Okay. Forest. Lots of trees. Yeah. Okay. So no cycles. A cyclic graph. Yeah. No cycles, and each node has only one parent.
Direct is the cycle.
Okay. Each node has only one parent, and the one which does not have parent, we call it. What's this? We call it what? Root. And the one.
Can't have more than one root.
Yeah. Excellent. Yes. And the ones we allow the kids, we call it. What do we call it? What are these nodes? 4, 5, 6, 7. Leaves. Yeah. It's actually like an upside down tree. Yeah. If you look it from upside down, that's the root. That's the branch. Or we call it trunk, and the leaf. A binary tree is basically like each node can have at most 2 kids. Okay, left and right. Okay, so today's question very easy. So we have a binary tree, and the binary tree usually you have this node, and then the node will have this value, and we have this left, and we have this right pointer. So now we're going to add one more field which called next. So initially the next pointer will be all initialized to none, and then we want you to populate the binary tree so that each node points to the next points to the one on the same level. Yeah. So basically, we want you to add one more link. Yeah. That's it. Do you get my point?
Yeah.
Yeah. Do you get my point? Yeah.
Yeah.
So we want to point the node to the next on the right, on the same level. Yeah. So basically, look, this is left and right. Yeah, left and right. But we want to add one more next, which is initialized to be none. But we want to point to the one on the right. Okay.
So the root does nothing.
Exactly. Okay. Because it does not have any nodes on the right of the root, right? Yeah. So so does it remind you something? The same thing, the node on the right on the same level. Okay, so what hint is that? Same level. So
Breakfast search.
where down? Breakfast search. Easy. So probably we can do this breakfast search, but breakfast search is the way to go, right? It's very obvious. So we just breakfast search, and then by taking, because look, the breakfast search actually we can implement in 2 ways. One way is that every time, look, this 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have a queue, DQ, double and DQ, yeah? Okay, so how do we do this? First of all, we put the node in, yeah? Look, 1. Okay, that's the initial state. Okay, I take 1 out, I take everything out from the queue because that's all the nodes in the queue is the same level. Only 1 node on the first level. And I push its kid. What's its kid? I take 1 out, yeah? What's the children of 2 and 3? Of 1?
2 and 3.
Yeah, okay, and I put it in, yeah? 2 and 3 in queue. Okay, so now look. All the nodes in the queue, 2 and 3. There are 2 ways. One way of breakfast search is I can take 1 node at a time. So I take the 2 out and then push the kids is 4 and 5 in. Or I can take the other way is I can take 2 and 3 out at the same time and push its kids. Because I know if I do it this way, I know at any time all the nodes in the queue belongs to the same level. Look, 2 and 3, same level, yeah? So how about that? I take the 2 out, 2 and 3 out, DQ, take it out, first in, first out, yeah? What's the children of 2?
4, 5, 5.
4 and 5. What's the children of 3?
6 and 7.
You see? Look, now 4, 5, 6, 7. What are these nodes in common?
Then same level.
We're done. Okay, then now I do the same. I take 4, 5, 6, 7 out, and I push the kids, which is 8 and 9, right? So I take these out, everything go out, yeah? So 4, 5, 6, and I put the 8 and 9. Look, 8 and 9, the same level, yeah? So if we do it this way, we can make sure all the nodes in the queue belong to the same level. Why do we need that? Because if we know that all the nodes are on the same level, then I can point this node to the one on the next. We want to put the node, put this green next. We want to put the node next to the one on the right, okay? So we want to add one more link from the node and to the one on the left, on the right, okay? So we will put the 4 to the 5, 5 to the 6, 6 to the 7, right? Okay, now we can do this breadth search. How do we implement the breadth search usually? You know this question? How do we implement the breadth search?
Q.
And in Python we can use the
DQ.
DQ, double NDQ.
Sandwiches.
What's sandwiches?
Sausages.
What's
Breakfast.
Oh yeah, BFS, breath means wide, yeah. As opposed to depth, okay. This is different, okay. Breath, depth, okay. Okay.
Breath.
Okay, now let's implement this breadth search, okay. Breadth search, okay. That's it. Define, let's say populate right, okay. Populate right, okay. And then given this root node, okay. So Q equals DQ. The advantage of using DQ as opposed to a list, you know, in Python we can use the list to implement a queue, right? First in, first out, right? But then if you go for this approach, the disadvantage of using that is as a queue is because the operation when we do this q dot pop 0, this is linear time, okay? As opposed to the q dot pop left, which is constant time, okay? DQ and root. So as the normal breadth search, while q, and we check n is length of queue. This is the number of the nodes in the current queue belongs to the same level. And then we can do this for underscore in range n. Then we do this current q dot what? If we want to take a node from the queue, first in, first out, what method is this? Q dot what? Pop what?
Left.
Pop left, yeah.
Left.
If we don't specify left,
Right.
then it will be the right, yeah? Q
Append
dot pop.
right.
Yeah.
Append right.
Append left. Look, Q dot pop without the left is right. Q dot append without the left is right, okay? If we don't say which way, it by default is on the right hand side, okay? Q dot pop. Okay, and then we have to do this. Look, this is the number of nodes in the queue, yeah? In the queue, like 1, 2, 3, okay? N is 2 nodes. Okay, and then we go to each node, then we pop it, we take a 2 out, then we have to check if current dot left, then we push it back, we append the left kid to the back to the queue. So q dot append current dot left. Understand? What's next? If what? Can you guess? If what?
Current dot right.
If current dot right, and then we do what? Append what?
Current dot right.
We're done, okay? And then now, look, we just pop it, and then append it, and then the most important thing now is to link it, to add this link, right? How many nodes we need to link? We need to add a link. 4, 5, 6, 7. Which nodes needs to be adding a link?
3.
Yeah. How many links?
1.
Okay, so which node does not need to add a link?
First one, root.
Yeah. But I mean the same level. Which node does not have to add a link? Let's take a look at the nodes on the same.
Far right.
Far right. The one on the right does not, because it points to nothing, right? Exactly. So then we have to check.
Points to.
Yeah. Okay. So we have to we have to use this index for I. Yeah. So if I not equals n minus 1, because if it's n minus 1 is the one on the right? Then we have to pop it. We have to link it. So what? Current dot next equals Q0. This is the thing today. Because all the rest is breadth search. Can you explain to me what if I when's the case when I is n minus 1?
Oh, 8.
If I not equals n minus 1, what does it mean?
If I means not
equals n minus 1, what if I is n minus 1, what does it mean?
It means if it doesn't point to anything.
Okay, so if I is n minus 1, it means the node is on the far on the right? So if it's not on the right, if far on the right, then we can point current dot next. This node points to Q0. What's Q0? Can you tell me what's Q0? What's Q0 mean? This is the Q. Q0 is what? So this is the Q. 1, 2, 3. There are 3 nodes in the Q. So Q0, where is it? Which one is Q0?
The first one.
Yeah, so it's the front of the queue, right? This is the queue. First in, first out. You go in here, you take it out here. Q0 is the front of queue. So here, look, if we are here, Q0, because we already taking top left, we take the 4 out. So the Q0 will be 5, right? If I'm visiting a 5, Q0 will be 6. So what this means is that I'm current, I point to the next pointer to the right, okay? Except the last one, except the node on the far right? Yeah? So this is the thing. All the rest is breadth search. The time complexity, O(n). N is the number of nodes in the binary tree, okay? The space complexity, O(n), because we are using the DQ. Got it? Okay, to sum up, what have you learned today? Come on.
Binary tree. Yeah.
No. What have you learned today? You need to explain to me in one sentence, not in one word or 2 words. Okay? So what we have learned today, what's the problem? And what are we trying to solve today? And what kind of approach are we taking
We're
today?
using breadth search.
Yeah, we using to do what? To solve what kind of problem? Come on.
So the binary tree. Q.
Yeah, come on. Don't give me a few words. I want a sentence, a whole sentence. So,
Okay, we got Q.
what's the problem? First of all, what's the problem?
The problem is I have hiccups.
Sorry, what's the?
We have a tree, obviously,
We have a binary tree, yes.
and then we're supposed to
What?
find the next number. Yeah, in the same level.
Okay, so we try to
Right.
we try to add the link to the right on the node on the same level. Okay. And what's the approach we're taking to solve
Q.
this? What's the approach?
Breadth
Breadth search, and we're implementing using a queue. Okay, so I give you an example. Yeah, next time I ask you this question, you can answer it like that. Okay, so today the problem is that we are given a binary tree and we want to add a link for any node, yeah, any node or in the binary tree to the one to its neighbor on the right in the same level. Okay, and the approach we're taking today is breadth search, because the breadth search is used normally to do this level by level traversal. Yeah? And when doing this level by level traversal, we add a link here, except the last node on the far right? Because it does not point to any neighbor on the right. There's no neighbors on the right. Alright? Yeah? Got it?
Yeah.
That's it for today. Thank you. Bye bye.
Bye.